In this video, we'll take a look at the mechanism for a Fischer esterification. If you have a carboxylic acid and an alcohol present under acidic conditions, you will produce an ester and water. Now you'll notice I wrote the water as HOH because the hydrogen will have come from the alcohol, the OH will have come from the carboxylic acid. Let's go ahead and take a look at this mechanism. Remember, the first thing is always your fundamental concepts. Do I have a negative or do I have a positive? In this case, I'm under acidic conditions. I have a positively charged oxygen, not a very happy oxygen. This is going to want to recoup these electrons right here. And now we have three options here. We have an oxygen here, which is slightly negative. We have an oxygen here, which is slightly negative. We have an oxygen here, which is slightly negative. And all three will get protonated at some point, but the one that's going to get protonated the most, the significant one, is going to be this one up top over here. And let's see why. Let's go ahead and pick up that hydrogen, protonate the oxygen of the carbonyl. We now have what some people call an activated carbonyl, an activated carboxylic acid. And this is now positively charged. And the reason why this one's the one that's preferred is because this can resonate now. We can actually resonate here like that. Those two electrons go up, going to draw a resonance structure, and the other ones cannot resonate. So, and this is, you'll also notice that this is going to be equilibrium. Now that one's positive right there. Equilibrium, because as soon as this happens, a water molecule, actually let me show the water molecule, plus an H2O. Actually, let me draw that up over here. And we have our, let's also go ahead and put the alcohol here. And we'll have H2O. And this water then can go right back and pick up the hydrogen from the protonated carboxylic acid and revert back, either that one or this one, and revert back. So this is going to be a series of equilibrium steps. At this point now, we have a activated carbonyl, very electrophilic carbon of the carbonyl. One of these is going to get sucked in, and for the esterification, again, all this is equilibrium. For the esterification, let's go ahead and have the alcohol get sucked in. Now I'm going to tag that alcohol. I'm going to fill that in. I'm going to go ahead and have it attack there. That way these electrons can go on there. And now, and this is also going to be equilibrium. I'll go ahead and we'll have this intermediate oxygen, a neutral oxygen, and the alcohol, bringing along with it the alkyl group. Now this alcohol right here, that oxygen, that's tagged that one. I'm going to have a lone pair over here, and this oxygen now is going to be positively charged. Now again, as soon as this happens, this oxygen is positively charged, and electrons from up here can come right back down, kick that out, and we're right back to here. We can also have the water molecule come in and do that and come out. So again, all this is equilibrium. At this point now, we have at least put these two molecules together. We have water from our acidic conditions. The water is going to go ahead and deprotonate this oxygen, that oxygen right there. These electrons then will come back onto here, and now we're going to have a neutral compound overall, where we have three OHs, three oxygens, each one of them neutral. This oxygen down here, boom, boom, that's the tagged oxygen that was originally from the alcohol. And we have our acidic conditions, our hydronium, and we have a neutral compound. But this is still under acidic conditions. And this oxygen can easily go ahead, get protonated and revert right back to here. Or one of these oxygens will get protonated. So again, this is going back and forth, back and forth. At some point, one of these oxygens here is going to go get protonated. I'll have this one get protonated. And now we have, let's see over here. Again, this is all going to be equilibrium. We have our compound here, one OH group up here, a protonated OH group right there. So now this oxygen is positively charged, and the oxygen that's tagged was originally from the alcohol is right there, and we're back to water. Now, as soon as that oxygen is protonated, again, once again, yes, this water molecule can come back over here, deprotonate, revert back to here, and again, all this is equilibrium. But at some point, as soon as this oxygen is protonated, at some point it is now it is at this point it's a really good leaving group. So we can have electrons from this oxygen come swing down and kick out that water. Again, all of this is equilibrium. And so now we're going to have this compound, this product right here. We have formed the carbon-oxygen double bond. This oxygen is now positively charged. We do have so now we have an ester. We have this oxygen, this is the tagged oxygen that was originally from the alcohol, and a water molecule comes out. And then we go ahead and deprotonate this. Now again, this is also equilibrium, because as soon as this happens, that carbon is very electrophilic. This oxygen wants to recoup electrons. So yes, this water molecule can go right back there and revert back to that. But this will go back and forth. And at this point here, at some point, then a water molecule will come along, deprotonate, and give us our final ester, where the original molecules now are one molecule here. Here we go, this, like that. Here's the oxygen. I'm tagging that oxygen. That was the one that was originally on the alcohol right up over here. I should have tagged that from the beginning. And then we're back to H3O plus. And so this is actually catalytic, because now that H3O plus can go ahead and protonate next carboxylic acid and go from there.